great to be here, and following up Andrew's talk, I think it's nice because he talked about this idea that I think has been around, as he said, for a while, that in cosmological simulations like these that produce disk galaxies that look pretty realistic, we see that galaxies like the Milky Way grow inside out, upside down. What I'm going to do today is talk a little bit more about why galaxies end up looking like this. And rather than talking about inside out, upside down, or even the velocity dispersion, we found it useful to think about the orbits of the stars and gas in the galaxy over time, whether they're very circular or very radial. And in this picture, the stars that are living along these sort of thin disk components are certainly very circular. They're living in sort of tight circles oriented along the plane. And then the other stars, the ones that kind of exist up here, are on orbits that are quite radial. And it turns out that there's a lot of structure in the history that's very regular if you think about that. And the thing that's remarkable is you also see the same kind of thing in the Milky Way itself. And Vadim talked about this, I guess it was Monday. It's incredible that you see this with Gaia Dei in the Milky Way. So that's sort of where I'm coming from. The big picture is, why do they end up looking like this? How do you make thin disk galaxies at all? And I would argue we don't really know, but we're making progress on why and what's happening. The work I'm going to talk about has been led primarily by 3 different people. The bulk of my talk is going to be work that was led by Olte Mertai, who's a PhD student at UC Irvine, and then another PhD student, Patricia Fofi, who just goes by Fofi. I'm going to talk about her work as well. And then finally, Luke Shah, who's here, is an undergrad. He's doing some really great work on galaxy shape, and I'm going to talk about that as well. So we saw this plot earlier that Vadim showed, and it's really this remarkable work by Chandra et al., looking at Gaia data for the Milky Way and demonstrating, look at the orbits of stars in the galaxy in terms of this circularity parameter, which is basically a ratio of the angular momentum to the angular momentum that star would have if it was on a circular orbit with the same energy. You see these 3 distinct phases of stars in the Milky Way. At low metallicity, stars are on pretty radial orbits, so you can think of this as a spheroid or inner bulge kind of thing. And then at intermediate metallicities, the stars are orbiting, but they're not super circular in their orbits, so they're spinning, but it's kind of a thick disk component. And then finally, after a characteristic metallicity that they called cool down, the stars snap to these very, very circular thin disk type orbits. So this is pretty remarkable. And the whole framing of my talk is, what's up with the cool down, and why do we have these 3 transitions? How did you go from this early spheroidal phase, spinning up into a thick disk phase, and finally cooling down into the thin disk phase? Why is this like this? And by the way, this is archaeological. And so we can ask, does this archaeological picture hold up if you can trace galaxies in time? And also, of course, this is metallicity and not time. Does that even work as a clock? So just starting off, if you take one of the Milky Way simulations that Andrew was already talking about, in particular, this is, I think this is Romeo, and you make the same plot and put it on the same color scheme as the same data I just showed you, it looks pretty remarkably similar, I would say. So there are these 3 distinct phases. There's an early proto-galaxy phase, there's the spin-up phase, and then the cool-down phase. Sort of see it in the same parameter space, we see this. And I'll show you in a little bit. We see these 3 phases this way for all 12 of the galaxies we've looked at. Of course, the characteristic metallicities are a little different, the transitions are a little different, but you see, generally speaking, these 3 phases. And so again, the question is why? So now I'm doing look-back time, the same galaxy Romeo, and you see that the same story holds if you do look-back time as metallicity, so that's nice. At early times, orbits are pretty radial. You have this kind of spin-up phase where they start becoming more circular, more rotationally supported, and then finally at late times, it's this thin disk phase with very low scatter in the circularities. The blue line is archaeological, the orange is young stars, and you see if you're just looking at young stars, it actually traces the archaeological picture fairly well. which is also nice. You can sort of think about this archaeology as really tracing back in time. Of course, there's been disk heating at late, etc. Finally, another thing that's kind of interesting is if you do the same analysis with gas particles along time, you find that the gas spins up slightly earlier than the stars, which maybe isn't surprising, but it's kind of interesting to track the gas in the stars, and we see this is also a general feature. So you'll have a period of time where you have a spinning gas disk, but the stars are random, and then then everything starts spinning together. Might not be surprising. I think people have probably seen this before, but just to sort of point it out. We see this three-phase evolution in all of the Fire 2 Milky Way suite that we've looked at. Again, the periods of time are sometimes the spin-up phase is very rapid, sometimes it takes a little bit longer, but generally speaking, things start off kind of with random chaotic orbits. They have co-rotating spinning orbits and then very thin disk orbits at late times. Here's something that's kind of cool too, is there seems to be pretty interesting correlations between the nature of star formation and the orbits of the young stars and gas over time. So, prior to the cool down phase, in these simulations, the star formation is bursty. So that's pretty interesting. After cool down, the star formation becomes pretty steady. Whereas prior to cool down, the star formation is bursty. Secondly, what I'm calling the star formation efficiency, which is really just the star formation rate divided by the gas mass in the system within the galaxy, it actually is highest during the spin-up phase. So it's low efficiency at early times, but even though it's bursty during the spin-up phase, it's actually efficient. And Luke is actually working on trying to figure out why. I don't know the answer exactly why. We think there's just more mass and dense clouds of gas that could be star forming at that time. And then at late times during this steady phase when the star formation is not bursty, it's kind of steady, marginally efficient, but not as efficient during the spin-up phase. So just the mere fact that the nature of star formation correlates with the orbital structure of the stars and gas that it's born out of is kind of interesting. It may be a clue to what's going on. So basically what we have here is we have this first phase where the star formation is bursty and low efficiency and stars are born on radial orbits. These stars tend to evolve into spherical components. Then we have the second phase where stars are spinning up. We still have bursty and very high efficiency star formation, which is kind of interesting. The thing starts to spin, but the orbits are tilted, and this ends up making your thick disk phase. And then finally you have this steady settled star formation in the late time phase. So first thing I'll ask is, why do these disks cool down? There's been a fair amount of work on that, but the answer that I like the most is that what's happening is the inner circumgalactic medium is virializing. So at late times, the inner circumgalactic medium virializes, it gets hot. And what this means is as the gas gets into the galaxy, it takes a long time compared to an orbital timescale. So that gives the gas time to become coherent and mix prior to joining the disk. So basically what happens is when the gas joins the disk, it's very well aligned already, and it just lands in the disk on circular orbits, and it allows this very thin disk to develop. Also, there's this hot pressurized circumgalactic medium around it, and that also helps kind of stabilize the burstiness. So this is work that we've sort of worked on before. But the question that I think is actually kind of more fun is, why did they spin up to begin with? And some ways you're going to get an answer that's a bit tautological. It's just that, like, you have lots of random motions, and the random motions are bigger than this, sort of tendency to spin, and that's why it doesn't spin up. To me, that's not quite enough. That's sort of like, that's just describing what it is. The question is, why does it go from this chaotic non-spinning phase to this spin-up phase? So one idea, so I was inspired by this paper that Phil wrote, which was great, where he put in, there's sort of semi-idealized simulations where one of the things he did is he just put in these potentials by hand and cranked them up, and found that in simulations where the central potentials are cranked up, you make disks. So if you have steep central potentials, you make disks, and if you don't make disks. So this makes a lot of sense. It's a very interesting idea that this could be driving what's going on. And the question is, if we just track these M12s with time and see if is that what's happening here? Does the central potential get cuspy and then the disk spins up? What we find is something that's actually pretty surprising, and in fact sort of the opposite is going on. It turns out that at spin up, so this is a measure of how cuspy the central potential is. The bigger this number is, the more puffy the rotation curve is, and the smaller it is, the more peaky the rotation curve is. So it turns out that almost at every time they spin up about the time where it's maximally puffy. So it's like the least concentrated is when things spin up. But after spin up, that's when something like baryonic contraction drives the rotation curves to become peaky, and subsequently they become concentrated. So the disks start to form, and then the rotation curves kind of get peaky, which is kind of interesting. And it could be that that is also driving inter-CGM virialization, because it's sort of all kind of happening at once. Instead, the thing that seems to be, at least the one thing we can find that seems to be correlated with this is that prior to spin-up, the baryons are sloshing around in the potential. That is, the center of mass motion of the baryons is not well aligned with the center of mass motion of the whole system. So one of the things that's happening is baryons are pouring into the thing rapidly. So the mass accretion rate is very high at early times, and it's actually the time scale of mass growth is shorter than the dynamical time within the system. So the thing just can't really come into equilibrium at first. And this kind of goes back to Reese's thesis work, where she showed that dark matter halos grow rapidly in the inner parts at early times, and then they slow up at late times. I think it's sort of one of the things that's kind of governing this. Along with the feedback, it's also kind of keeping this thing sloshy at early times, which I think is going to affect all low mass galaxies. So that's kind of an interesting trend. And so the story that sort of we're at least right now, is you have this early phase. During this early phase, it's a pre-chaotic time. Mass is pouring in so rapidly that the system can't respond. It's kind of, the feedback is pretty strong, and the baryons are sloshing in the potential. But once that slows down, the system has now something to orbit around. And this was the point that Phil made in his paper. That now you have a center, and now that you have a center, you can start to orbit around. And once that happens, the central potential starts getting concentrated. The inner CGM virializes. And when that happens, the orbits become razor thin. And you have these thin disks that start to be made. So I don't know if this is actually what's going on in the real universe, but this seems to be what's going on at least in these simulations, which kind of look something like Milky Ways. So it's an interesting story that we're starting to piece together in terms of how these galaxies spin up. So Fofi comes to me and says, hey, I'm really interested in AGN. What happens when AGN get in the mix? And I was like, I don't know. So she was like, let's look at it. And so we took several runs, but in particular I'm just going to pick out two. This is from a paper by Wellens et al., where she looked at lots of different sort of AGN feedback recipes within fire. And this is that works pretty well in landing on the right M-star and halo relation and quenching galaxies the right way. So here's M12I with no AGN, and here's M12I with this jet AGN model. And what you can see sort of by eye is it is pretty quenched, because it sort of slows down star formation. The disk component's drastically suppressed, and it looks kind of like a spheroid with a very bright center. So you might ask, okay, well, I had this nice story of how galaxies' morphologies evolve. Why does the morphology change when you have AGN suppressing star formation? Why does it now, what happens to this story? So first of all, around 8 billion years ago, the thing starts quenching. And so then you can ask, what happens to the orbits of young stars, the orbits of things as this evolves? Well, if you look at the orbits of all stars, this is just circularity, this early rapid chaotic phase. Then they start to spin up, but the AGN model just doesn't spin up as much as the no AGN model. Okay? So we get that from the picture. But one thing that's really interesting is if you look at the orbits of the young stars, throughout the whole time, it just tracks. So at late times, the young stars are forming on a thin disk. The problem is there's just not that many young stars. The young stars that do form make this sort of weak disk component, but there's just not that many of them. And so they just get swamped by the old stars that were there earlier. So this is just one example. We have a few others that we're looking at. But it's just kind of fun to sort of track kind of star by star, orbit by orbit, to sort of see why the morphologies build differently. And there's nothing to do with mergers. And it turns out that when there are mergers that play major roles, it's very counterintuitive in terms of what's happening here. So I'll leave that there. Okay, finally, I wanted to talk about what's going on before stellar spin-up. Because in some cases, this process lasts a long time. In particular, Thelma's one that has a really long phase before it starts spin up. So it turns out for this project, this is one to sort of focus on at first. And this is the thing that Luke is working on, which is shapes. So people have seen this before. This is the C over A versus B over A space where you can characterize galaxies in disky, elongated, or spheroidal, depending on what the axis ratios are. So what's shown here is the shapes of young star populations in this galaxy as a function of look-back time. So they're color-coded by look-back time. And so when the thing becomes kind of purple there, anything yellower than that means it was formed during this chaotic phase. And what's interesting, and we sort of heard a little bit about this before from Ropsock, this Milky Way progenitor spends a fair amount of time in a phase that looks like an elongated pickle. And sometimes it's more spheroidal. And this is all during this chaotic phase. In fact, it spends about 30% of its time prior to spin-up with this elongated shape, which is kind of interesting. And if you look at those same stellar populations today, they're very round. So one of the things you can kind of tell if you track over time, but sort of obviously from this, these are not stable configurations. So stars that form looking like a pickle are just spheroids today. So they're very, very round today. So what this suggests is that these elongated phases are not long-lived. They're sort of transient phases. They very quickly get out of that. And if you just wait over time, everything gets mixed up and it just becomes kind of spheroidal components today. So, here's some just pictures sort of showing that. Here's a snapshot of young stars that say in the middle here is Z of 0.7. This is where these stars are today. So you're looking at the pickle edge on, and then from the other edge here, so it's sort of rotated like this. You're looking at the pickle like this. Now you look at it from the same two angles, it looks much rounder. Of course, the stars that formed in a disk are still in a disk. And the stars that formed in this particular epoch, which is more kind of chaotic and roundish, are very round today. So that's summarizing this. But the upshot from this analysis was that the young stars in Milky Way progenitors prior to spin-up are spending about 30% of their time in this elongated phase, that those stars relax to a very round shape today. And Luke has a whole paper on this. If you have questions on this, you should talk to him over the break. So, conclusions. It looks like these Fire 2 disk galaxies evolved through these three kinematic phases, which are very reminiscent of the three kinematic phases we see in the Milky Way. The first phase is this bursty random phase. Sometimes described in these kind of elongated shapes. That stuff evolves into a spheroid component today. There's a second phase which is also bursty, and the star formation efficiency is high, and the thing is rotating, but not razor thin. That evolves into the thick disk today. And then finally, there's this steady, settled, very snap-aligned phase where the stuff turns into a thin disk. It seems like the spin-up phase, this transition, requires a stable center of mass for stuff to orbit around. Maybe that's obvious, but it sort of seems to be happening. And the settled down phase seems to require slow accretion of gas from the CGM. And allows you to have this angular momentum coherence. So, and that might be sort of enabled by the fact that potential is getting very steep when these disks start to form. Okay, that's all. Thank you.
Beautiful. I want to make some comments that Avishai would probably make if he were here, because it's work that I did with Avishai.
Yes.
So, first of all, it seems to me likely that your bursty pre and current spin-up phase corresponds to the transition from below and above the Deckel-Bernboim magic mass of the halo, about 5 times 10 to the 11. If you're below that, the gas is going to come in on cold streams. That almost always means it's going to be chaotic and bursty. The spin-up occurs, as far as this transition from the radial orbits to the more circular orbits, what we found is, and surely this is what you're talking about, and this is also Phil Hopkins' point, when you've got a massive center, basically because you get a compaction event, is what we would call it, that converts, that makes the radial orbits very energetically disfavored, and it turns them into circular orbits. So that's what's going on according to our simulations. I think it agrees with what you're doing. And then there's this Danovich et al. Paper 10 years ago. And what that's saying is that once you've got a disk, the incoming gas is going to be torqued down into the plane of the disk. So two things. One, you've got the gas now coming in much more organized angular momentum. And secondly, and this is the key point that your fire papers have been making, the gas has now been shock heated. So it can't cool quickly and become turbulent. Instead, it cools slowly. It gets a chance to get coherent rotation, and that's the key step for making thin disks. Big question. There are other simulations like TNG that don't look like that at all. Are they doing something wrong, or is there some different story?
I mean, from what I understand, so the question about TNG, and there's probably people here, yeah, okay. So I guess what I would say is, I think they looked in TNG and they were not able to conclude whether or not, it was sort of everything was kind of happening at once. It did look like they were getting virialized inner CGMs when the disk started spinning up. I think the issue with TNG is they basically can't fully resolve whether or not the stuff is a super thin disk or a thick disk. I could be wrong about that, but I think this distinction between the thick disk to thin disk phase is a little harder to reconcile if you've got a thicker kind of ISM. It could be a resolution. It could be the nature of the ISM simulations in those simulations. Yeah, but I mean, I think it'll be interesting to sort of track this down and see. But I agree. I think there's a lot of similarities between what you guys have been doing for 10 years and what we're finding. I mean, I think the story is becoming pretty coherent. We did not really see the compactification being the thing that drove the spin up. It was more like the thing started spinning up and then it got compact prior to the thin disk, which is surprising to me, but it seemed like it's sort of the opposite, and I was still a little bit surprised by that. And I'm not saying it never happens, but for the bulk of cases, the things are actually very puffy in their potentials and not compact when the thing starts spinning up, which is a little surprising. So yeah, a couple more.
Yeah, so we are getting very close to the next session. So it's 11:45. So if this is a quick question, we can have a quick answer. Not very quick? Okay. Is there a quick question here?
Is the right way of thinking about this is before spin-up, that the angular momentum is actually not well defined and not conserved, because you don't really have a point to which...
I think that's fair. I think that's a fair way of saying it, that prior to spin-up, there's really not a center to orbit around, and so it's not even clear how to define it. It's just a mess, yeah.
Okay, well, let's thank James and the other speakers.